Now that we learned about tables and graphs for categorical data, let's learn about tables and graph for numerical data. For numerical data, we have ordered array, an example of which is a stem and leaf display, which is a very trivial and basic way to represent numerical data, and also archaic. Also, we're going to learn about different frequency distribution and cumulative distribution types of charts for numerical data, an example of which is histogram, polygons, and ogives. Organizing numerical data using an ordered array. What is an ordered array? An ordered array is just a simple way of representing data. We're going to organize the data from the smallest value to the largest value in an ascending order. An ordered array can show us the range of data, the minimum value and the maximum value, and everything in between. Ordered array can also help us to identify outliers if we have any. Outliers are unusual observations. We're going to learn about outliers more later in the course. So let's see an example of an ordered array. Here we have the data for the age of students for two types of classes. We have day shift students and night shift students. So we have ordered the age of these students, that the data that we have, from the youngest to the oldest for these two types of classes. So here we have the youngest student in the day shift classes is 16 years old, and the oldest student in the day shift classes is 42 years old. For the night shift classes, the youngest student is 18 years old, and the oldest student is 45 years old. A stem and leaf display is just a simple way of representing numerical data. We are basically going to create two columns. One is called the leaf, and the other one is called the stem. We put the last digits of the numbers that we have in the leaf column, and every other things in the stem column. If we then draw a line over the top of the leaves column, we're going to get an idea of how the frequency graph for our data would look like. This may sound difficult, but actually it is very easy. Let's look at an example. Suppose I have this set of data. So I have these 2-digit numbers, but they don't have to be 2 digits. Let's create a stem and leaves display for this. First, I'm going to create a stem column. So this is the stem column. I'm going to fill it with digits of 0, 1, 2, up to 9 from top to bottom in an ascending order. Then I'm going to create the leaves column for this. So this is an stem and display. But how does this really work? Let's look more closely to this. So I don't have any numbers with 1 digits. That's why I don't have any leaves in this row here. I don't have any numbers with tens, right? So that's why I don't have any leaves in this row. No numbers in 20s, so no leaves here. I have 36 here. So I'm going to put 6 in this column. I don't have any number in 40s, so no leaves here. I have 58 here, so I put 8 in the leaf column for the 5. I have 62 and 68 here. So for 6, row 6, I'm going to put 2 and 8 here. And this is how we do it for row 7, 8, and 9. If we then draw this line here that you see, that's going to cover the leaf section. It's going to give us an idea of how frequent the numbers that we have is. For example, row 8 here, as you see here, it has more leaves. So that means that The 80th number is the most frequent number that we have. So as you see here, it's actually very easy to develop a stem and leaf display. I'm going to erase these lines here. A frequency distribution table is a summary table in which we organize the data into numerically ordered intervals, and then we keep track of the frequency of each interval. Let's see an example. Suppose we have this set of the data. The data are 12, 13, 17. As you see here, they are ordered in an ascending order. So let's build a frequency distribution table for this. This table includes two columns. The first column is called the bin or category, and includes intervals from 10 to 20. This interval includes 10 but not 20. The second interval is numbers equal to 20 and greater than 20 but less than 30. The third one is all the numbers between 30 and 40, including 30 but not including 40, and so on and so forth. The second column keeps track of the frequency of the numbers that we have for each interval. So let's see. For example, for the first category, the numbers between 10 and 20, how many numbers do we have in this interval? We have 12, 13, and 17. That's 3. So we have 3 numbers. The frequency of this interval is 3. For the next interval, 20 and 30. Between numbers between 20 and 30, how many numbers do we have? We have 21, 24, 24, 26, 27, and 27. That's 1, 2, 3, 4, 5, and 6. So we have 6 numbers here. 6. And we continue with this until we fill out the frequency distribution table. Let's see. I'm going to get rid of these lines here. All right, we are done. What we need to make sure is we should have the same number, the total number of the data that we have, which is 20 here. The total frequency should be equal to the total numbers that we have here. Organizing numerical data using a histogram graph. A histogram is a special bar chart. Let's see an example. So this is the frequency distribution table that we created for the previous example. Let's build the histogram graph for this. So as you see here, a histogram is just a bar chart. Each bar represents a bin, a category or interval. For example, this bin or interval from 10 and 20 is represented by this bar here. We show it by 15 because that's the number between 10 and 20. The frequency of this interval is 3, so that's the height of this first bar. The next bar, this bar, shows the next interval. That's the interval between 20 and 30. The frequency of that is 6. So this bar here, the height of it is 6. And it is shown by 25 because 25 is the number between 20 and 30. So we're going to keep doing this for all the intervals and their frequencies. And then we're going to have a histogram. See that we don't have any number between 0 and 10. So that's why there is no bar here. Also, we don't have any numbers more than 60. So that's why we don't have any bar here. And that is a histogram. There is another version of the histogram, which is called the relative frequency histogram. Let's build a relative frequency histogram for our previous example. So we have this frequency distribution table. Next, we need to create the relative frequency of each bin or interval. How is this built? For the first interval or bin, numbers between 10 and 20, the frequency is 3. The relative frequency for this interval is the frequency 3 divided by the total frequency 20. 3 divided by 20 is 0.15. For the next one, numbers between 20 and 30, the frequency is 6. The relative frequency would be 6 divided by 20. That would be 0.30. And we're going to continue this for all the numbers that we have, and they all should add up to 100%. 1. Next, we're going to create the histogram, the relative frequency histogram. It's the same as before that we have, except that for the vertical bar, for the vertical axis, or y-axis, instead of frequency, we have the percentage or the relative frequency. For example, this bin here, numbers between 10 and 20, the relative frequency is 15%, 0.15. So this is this bar. And this bar, the frequency of that, the relative frequency of that is 0.15. And we do that for all other bars as well. And we're going to have a relative frequency histogram. Another way of representing numerical data is using a frequency polygon. A frequency polygon represents data, each bin or category, intervals of data, using dots that are connected. Let's build a frequency polygon for our previous example. So this is the histogram that we built. To convert this to a polygon, we need to represent each category or bins by a dot. So we don't have any numbers between 0 and 10. That means that the frequency or the percentage for that is 0. So this point is 0 here, the frequency for this interval. We have for the next bin, which is the numbers from 10 to 20, which is represented by 15, the midpoint of this bar is here. For the numbers between 10 and 20, which represented by the bar 25 here, the midpoint for this bar is here. So if we do the midpoints of each bar, and then we don't have any numbers more than 60, the frequency for that would be 0. And now if I connect these dots together, I'm going to have a frequency polygon. This is a frequency polygon. Let me get rid of these dots and lines here. So as you see here, a polygon just uses dots and lines to represent data instead of bars. Graphing numerical data using an ogive, which is also called a cumulative polygon. Let's see an example how this works. This is the relative frequency distribution table from our previous example. To graph an ogive or cumulative polygon, we first need to build a cumulative relative frequency table. How it works? Let's see. This is the cumulative frequency distribution table. If you look at the classes here, they are cumulative, they add up. So the first class in our frequency distribution table is between 0 and 10. The first class in cumulative frequency table is less than 10. So we have 0% here, 0% here. The next class, to build the next class, Here we have between 10 and 20. But we want to build the second row here. We have less than 20. That means it includes the previous as well. Less than 20 means between 10 and 20 and between 0 and 20. So as you see, it's cumulative. It adds up to the previous one. The cumulative percentage for that is 15%. Let's build the next one. The next one would be, so here we have between 20 and 30. We're going to have less than 30 in the cumulative frequency distribution, which includes between 20 and 30, between 10 and 20, and between 0 and 10. So it includes all of this. It's cumulative, it's adds up. So the cumulative percentage would be 0 plus 0.15 plus 0.30, which is 0.45 here. I'm going to do one more. So the next one is less than 40, which means it includes numbers between 30 and 40, between 20 and 30, between 10 and 20, between 0 and 10. And the cumulative percentage would be the summation of all of these. 0 plus 0.15 plus 0.30 plus 0.25. And that would be 0.70. So if we keep doing this, we're going to have all of the numbers covered, 100%. Now that we have the cumulative frequency distribution table, we can build the OGIF, which is a cumulative polygon. If we actually build a polygon for this table, it's going to be a cumulative polygon, which is also called an OGIF. So as you see here, the first class is less than 10 here, with 0%, 0%. The next class is less than 20. The cumulative percentage is 0.15. The next class is less than 30 with cumulative percentage of 0.45%. So 30, 45%. And we connect all of these dots together and we build 100% of our data. So this is a cumulative polygon or an OGIF.